Good morning to all. Today I am presenting our project. Our project is MRI based early detection and multi-stage classification of Alzheimer disease using a hybrid CNN LSTM deep learning model. The project is done by Mageshwari M and Sangeetna V under the guidelines of Ms. M. Umalata, Assistant Professor, IT Department. Alzheimer disease or AD is the leading cause of dementia worldwide. It causes a progressive cognitive decline and neurodegeneration. With the global aging population growing rapidly, Alzheimer cases are rising year by year. Early detection, especially at the middle cognitive impairment or MCI stage, is a very critical for effective treatment. However, the current method depends on subjective assessment and costly imaging like PET scans. This is where MRI comes in. It is non-invasive, accessible. Our project leverages the hybrid CNN LSTM deep learning model to detect and classify Alzheimer's stages using MRI data. History and background. Let's look at how the Alzheimer disease evolved over time. Initially, only the cognitive and memory tests were used. Later, MRI and PET scans were introduced. But traditional image analysis are still relied on radiologists, which is subjective and time consuming. As the medical data grew, the manual analysis became inefficient. Researchers identified the brain atrophy, especially in hippocampus, a key indicator. Machine learning techniques like XVM, decision tree improved basic classification. Finally, the public data sets like AD&I, Alzheimer's disease neuroimaging initiative accelerated deep learning research in this field. Objective. Our project has 4 core objectives. First, pre-processing MRI images from the AD&A dataset using resizing, normalization, noise reduction, augmentation. Second, developing a hybrid CNN model that captures both spatial features and sequential dependencies for accurate multi-stage classification. Third, integrating this model into the clinical diagnosis support system for automated stage-wise classification. And fourth, validating the model or unseen data to ensure robustness and real-world reality. SDG goals. Our project aligned with the 3 United Nations Sustainable Development Goal, the SDG 3, good health and well-being by enabling early diagnosis and improving the patient quality of life. SDG 9, industry innovation infrastructure by promoting AI-powered innovation in medical imaging. And SDG 17, partnership for goal by encouraging a collaboration between the radiologist, neurologist and AI researcher to bridge the gap between the research and clinical application. Problem statement. The core problem is current Alzheimer diagnosis methods are subjective, time-consuming and requires expert involvement. PET scans are expensive and not easily accessible, especially in resource-limited settings. This causes significant delay in diagnosis. Early-stage Alzheimer is particularly hard to detect without advanced image analysis tool. Additionally, many existing AI systems are trained on limited data sets like Kaggle, which affects their real-world generalization. Existing system. The existing system for the Alzheimer diagnosis primarily rely on PET scan, cognitive assessment, and clinical interviews. While some AI-based approaches using the PET data have shown promising results, but MRI is not yet widely adapted for automated early stage detection in clinical practices. These systems also require high-ended hardware and expert supervision, making them impractical in low-resource healthcare environment. Proposed system. Our proposed system address these limitations. We use MRI data, which is more accessible and non-invasive than PET scans, and leverage the public data sets like ADNI or OASSI for the training. The architecture uses CNN layer to extract the spatial features from the brain images and LSTM layer to capture the sequential relationship across the image slices. This hybrid CNN LSTM model improves the classification by combining both spatial and temporal learning, achieving accurate and efficient multi-stage Alzheimer disease classification. System architecture. This slide shows the overall system architecture of our model. The pipeline starts with raw MRI input, which goes through the pre-processing step like resizing and normalization. The processed image then passes through the CNN layer for spatial extraction, feature extraction, followed by the LSTM layer that model sequential pattern. Finally, the output layer classifies the input into one of the four Alzheimer stages: non-demented, very mild demented, and moderate demented. And the project code will be explained by my teammate.
So this is our code for a pipeline of Alzheimer's disease image classification using CNN plus LSTM hybrid model. So I will walk you through the code. So first thing, we are looking at libraries where we are seeing the NumPy, TensorFlow, layers like CNN, LSTM, and the callback layer and class weight. So the first thing, NumPy handles the arrays and the TensorFlow keras are used for building and training the model. The layers of convolution 2D LSTM is used for neural network components, and the callback is used for controlling the training of data using the early stop for saving the best model. And the class weight is used for handling the imbalanced dataset. So the next step becomes under the configuration, where we are using image size of 128 cross 128, which is used to resize the images. And the batch size, we are using 32 images per step. And for training, we are using 30 epochs, which walk through the whole data set for 30 times. And next, we are going to check out the GPU. So if the GPU is available, it will be helpful for faster training. Otherwise, it will run on the CPU itself. So the next thing is loading the data. So which is automatically loads the data image folder from the folder name of class labels. So we are using the mild demented, moderate demented, non-demented, and very mild demented. So for these four folders are called as four classes. So using the data equal to tf keras utils image data set from the directory, it will take the path of the data where it is located. And then we store the classes as a labels and counts the number of categories available. So we are using here is a four classes. So next things we comes under normalization, where in normalization it converts the pixel values from 0 to 1 to 25 to 0 to 1, where it uses only 0 or either 1, and helps the model learn faster and more stably using the 0 and 1. So the next steps comes under training, validation, and test splitting, where we are using the 70% of data for training and 20% of data for validation. So here you can see the test and validation size. After that, we will split the final 10% of data for testing. Next steps comes under class weights, which is very important step, because medical data sets are imbalanced. Example, more non-demented will be available than moderate demented data sets. So class weights is very important to the rare classes. So it helps to prevent the bias towards major class. So the next steps comes the architecture of model building. The first thing is we are using the CNN for feature extraction, where it has the 32 filters, 64 filters, 128 filters. The 32 filters is low level feature extraction, and the 64 filter is used for mid level feature extraction, and the 128 filters used for high level of feature extractions. Also, we are using the reshape layer to get the original shape after the CNN process executed, and it converted to the batches of 16. So this prepares data for LSTM. So the next thing comes under LSTM layer, where it uses to learn the sequential dependencies. So it treats images features like a sequence, which helps to capture the spatial relationships better. So the next layer comes under classifiers, where we use to classify the layers of the dataset. So the layers will be fully connected. So using the softmax, we outputs the probability of each classes either 0 or 1. So the next things comes under compilation of the model. So where the model dot compile execute the model and runs each approaches. So the Adam optimizer is used for efficient learning, and the loss function is used for multi-class classification, where we are using 4 type of classes. And then last, metrics equal to accuracy used for tracking the accuracy of each model training. And then we comes for callbacks, which is a smart training, where we use early stopping and a model checkpoint. In early stopping, we use as a validation loss doesn't improve, because if the training overfits, it used to prevent that overfitting and stop the training if validation loss doesn't improve. And the model checkpoint is used for saves the best model automatically. The next steps comes under training. So we use feeds training data, where model.fit is used to validation the data to monitor the performance, and it applies class weights its callbacks. The final thing is testing, where we are using the print statement to check our accuracy. It evaluates the final performance on unseen data. The final thing is saving our best model. We save our trained model for later use. We can use it for loading for production and the deployment. So using the .h file, it will be stored in the processed of whole model clearly. So this is a code after we run the model. So this is our terminal, where it will show us the layer type, where convolution 2D, and the output of the shape and the parameters. So these are the parameters and output shape and the layers. So for each process, the 140 or 140 times it runs. So it runs up to 30 approaches. So here you can see the .h file trained model, which will be in binary form. So using the file of the model, the .h, we can implement this for full stack development, and give our model for predicting the uploading a data of MRI scans. So this is how our project is built and developed. Thank you.